Right, question 2. This question is about stationary waves. We have a microwave oven, we've got the transmitter here, it sends the microwaves over here, and they bounce back and they form a stationary wave in the middle. Suggest how stationary waves are formed in the microwave oven. So you need to know the definition of, or the circumstances under which a stationary wave are created, and it's when two waves of equal frequency are travelling in opposite directions. How can they go in opposite directions? Well, they come in here, they bounce off this wall, and they come back. So that's the first thing we need to say. So microwaves reflect off the oven wall. And then, we have two waves of equal frequency traveling in opposite directions so they interfere, keyword there, and form a stationary wave. Okay. Right, so what we need to do here is, as the student removes the turntable and places this chocolate bar, it's going to melt in these 3 points. So we've got to realise that a stationary wave is being formed, and the place where it melts is the place where we're going to get antinodes. So that's when we've got maximum amplitude. So here we're going to get a node, here we're going to get a node between the two antinodes. So we're going to get a stationary wave looking a little bit like this. So the microwaves are going up and down like that, and here they're going up and down the most, and here they're going up and down not at all, because they're interfering. So suggest why it only melts in the positions showed. So the positions it melts at are where antinodes, oops, don't go off the side, are formed. They have maximum amplitude and therefore maximum energy in the standing wave. So you should have done an experiment where you've seen standing waves form. This bit here is where the string, or well, in this case a microwave, but in your experiment it will have been a strings going backwards and forwards at the highest speed. Here it's just basically sitting still. Here it's going the most distance, so that's where it's got the most energy. Okay. Calculate by making a suitable measurement on figure 4 the frequency of the microwaves in the oven. So we need to find out what the wavelength is. So the first thing we need to do is we need to measure between two of these antinodes, but you always are going to end up measuring the furthest distance that you possibly can. So you could measure from there to there, but you shouldn't. You should always measure, sorry, so let's draw through that in the middle like that. We'll draw through that one in the middle like that. It's slightly off centre there, it's not perfect. My photocopies are slightly different size to the ones that were printed for the real exam, so I'll get a slightly different answer to the one in the mark scheme. So I've got 115 millimeters, 115 millimeters. So I've measured there the distance between the centre of that and the centre of that antinode. Now that is one full wavelength. It's because you're at a maximum here, down to the bottom, back to the top. So that's one wavelength going from there to there. So to get from an antinode to the next antinode is half a wavelength, to the next antinode is a full wavelength. So you've got to make sure that you realise that lambda is equal to 0.115 meters. So that should start us off. And then the rest is dead easy. We just use V equals F lambda. So we're trying to find frequency. So F is equal to V divided by lambda. So F is equal to, it's a microwave, so it travels at the speed of light because it's part of the electromagnetic spectrum. So 3.00 times 10 to the 8 meters per second divided by the wavelength, which is that distance there. So 0.115. You can find the speed of light if you can't remember it off the top of your head. It's on your formula sheet. It's the very first thing on your formula sheet. There. So put that into your calculator. You get 3 exponent 8 divided by 0.115. Press the E and G button to make it into a nice number. And then we have 2.60869 ... times 10 to the 9. So look at sig figs here. We've measured that to 3, and we've got the speed of light in a vacuum on the formula sheet is to 3. So we can put this to 3 sig figs as well. So this is 2.61 times 10 to the 9 hertz to 3 SF, like so. Explain why most microwave ovens contain rotating turntable in which the food is placed during cooking. This is pretty obvious now we've done the rest of the question. It's to make sure that we don't melt the food in particular places and not cook it in other places. So to cook the food evenly, we continually change the position of the nodes and antinodes by moving the food. So that's to stop any particular place getting far too hot or far too cold.